welcome to our last lesson of Chapter 9. This is 9.3, Separation of Variables. So in this section, we're going to be solving differential equations. And that means we'll be given a differential equation and we have to figure out what equation y would actually solve that, would be the solution to that. It would be both general solutions and particular solutions. In general solutions, you will have some equation that also has a c in there because you don't have enough information to have your particular solution. A particular solution means that you've been given some sort of initial condition that you can plug into your general solution and solve for c, for your constant. Okay? And so because our differential equations have dy dx's or y primes, they have derivatives in them, we're going to need to do some integration to be able to work backwards towards our initial y. Okay? So our y is our function or our f of x that would actually work in that differential equation. So finding the equation that if I take the derivative or the second derivative, can I get back to my differential equation? Okay. These ones are called ordinary differential equations. And if you're planning on taking some sort of not calculus, if you're taking engineering, computer science, physics, most likely chemistry, statistics, math degree at post-secondary, there's an entire course on differential equations. And the first one that you usually take is ordinary differential equations. It's usually a second or a third year math class. And so this is really just a peek at what that is. Okay, this is like a small taste of what you would look at in that course. And if you plan on taking even more, you can start going into non-ordinary differential equations, etc. I personally only took the one course and then went towards some different directions because at university it was not my favorite, but some people love them. So we're going to start with a procedure for solving a first order differential equation. Okay, so that means that you have only a first derivative. Okay, and your differential equation could be written in this form: m of x plus n of y dy dx equals 0. So you have some function m that is written in terms of x, another function n written in terms of y, times your derivative dy dx equals 0. M is a continuous function of x alone, and n is a continuous function of y alone. For this type of equation, all x terms can be collected with dx and all y terms with dy, and a solution can be obtained by integration. In other words, you're going to get all your y's, including your dy on one side, all your x's, including your dx on the other side, and then you can integrate. Okay? Such equations are said to be separable, meaning we can separate our x and y, and the solution procedure is called separation of variables. The steps are as follows. So if you're given an equation in any of these forms, okay, we can integrate to obtain the general solution. So you can integrate your m, which is in terms of x, including your dx term. You can integrate that term separately from your n term, which is in terms of y, including dy. And then if you integrate a 0, you would just get a constant. Okay. If you have the m and the n separated on opposite sides of the equation, you can integrate on each side of the equation. Okay. Usually that's what we do. We usually try and put all the y's on one side, all the x's on one side, dy goes on the side with the y's, dx goes on the side with the x's, and we integrate from there. Usually when we integrate, we add the constant on the y side. Okay. And the x side, and then we move everything together to get one new c value that usually is on the x side because we're trying to write our equation as y equals. So let's try some. So we want to find the general solution to this differential equation. General solution means we're looking for what does y equal. Okay. You should have a plus c in there somewhere because you don't know the particular solution. You do not have an initial condition. Okay. So step 1 is to separate the variables. This means you want all y's and dy on one side, and you want all x's and dx on the other. Okay. So first, if we take a look at this, I can move the x squared plus 4 over to the right. So I'm going to have dy dx equals xy over x squared plus 4. And I can tell by looking at this, the dy is going to need to stay on the left because it's on the top. The dx we're going to need to move to the right because it's on the bottom. So if we do that, we get dy equals xy over x squared plus 4 dx. Now we have this y on the right. It shouldn't be. It needs to be on the same side as my dy. So I need to divide both sides by y. And I get 1 over y dy equals x over x squared plus 4 dx. So that's step 1. Okay. So steps above, it said express the given equation in the differential form, and it gave us one of 3. We have expressed it in this form here, where we have y's and my ny on the left, x's and my mx on the right. Okay, so step 1, separate the variables. Step 2, integrate both sides. So when we integrate the left, we're integrating with respect to y. When we integrate the right, we're integrating with respect to x. Now, if I integrate the left, my antiderivative of 1 over y would be ln y plus c. That would be the absolute value of y because y cannot be negative. On the right, you're probably going to need substitution. So I'm going to do my substitution just off to the side here. Okay. I'm going to say let u equal x squared plus 4. So then du is going to be 2x dx, or 1/2 du is going to be x dx. So I'm going to end up with 1/2 the integral of 1 over u du, which is going to give me ln y on the left and 1/2 ln u on the right. Do not forget c. If you are writing an AP exam and you forget c, they'll stop marking. Okay? You have to make sure you include c. Okay? Constitutive integration is necessary. Now we're trying to isolate for y. Okay, so if possible, okay, if possible, solve for y and simplify. Now, it is important to notice that these two c's are not the same. So if you want, you can add c1, c2, like add a subscript here. So my first step in isolating for y is going to be moving my c1 to the right-hand side. So I'm going to have ln y equals 1/2 ln u plus a new c, where c3 is c2 minus c1. Now, recall that e to the ln x is equal to x. Okay. So we would have here absolute value of y is equal to e to the 1/2 ln u plus c3. This is the same as saying e to the 1/2 ln u times e to the c3. We need to replace our u back in here at some point, so we can do that at any time. I'll maybe actually decide to do that here. Let's add our x squared plus 4 back in here. And so then here I'm going to end up with my x squared plus 4, and I'm going to change that 1/2 to be an exponent, bring it back in. You don't have to do that part. And so a reminder here, e to the ln x is just equal to x. So that means that e to the ln x squared plus 4 to the 1/2 is going to equal x squared plus 4 to the 1/2. We can change that if we'd like. Okay. And I'm going to also say let k equal e to the c3. So I'm going to make a new constant k. This is going to give us y equals x squared plus 4 to the 1/2 times k. It's probably better practice to put the k in the front. We could also leave it as ke to the ln x squared plus 4 to the 1/2. You could leave it like that, but this last row here would be considered a better solution. We also don't really need these absolute values anymore. These could just be changed to brackets because it's the 1/2. It has to be positive in the inside. Okay, and we're done. Okay, the next one is given the initial condition, find the particular solution to the equation. Now, since you have an initial condition, this means you're not going to have any C's in your answer. You're going to use that initial condition in wherever you have X's and Y's to actually find C. Okay. So again, first step is to separate variables. Okay. Get all your X's on one side, all your Y's on one side. So I personally would start by moving this term over to the right and maybe rewriting this in terms of a positive exponent. So I'm going to have 1 over e to the x squared. Y squared was 1 dy equals negative xy dx. I can move my y from the right over to the left by dividing by y. I can move my e to the x squared from the left over to the right by multiplying by e to the x squared. So I'm going to have y squared minus 1 over y dy equals negative x e to the x squared dx. Step 2 was to integrate both sides. So if I integrate the left and integrate the right, on the left, I'm going to try and fix this up a little bit. I'm going to rewrite this as the integral of y squared over y dy minus the integral of 1 over y dy, or in other words, the integral of y dy minus the integral of 1 over y dy. On the right, I'm going to take the negative out, and I'm probably going to need to use u substitution. And I'm going to do this off to the side. I'm going to say let u equal x squared. So du is going to be 2x dx, or 1/2 du is going to be equal to x dx. This means I can take that 1/2 out and integrate e to the u du. This is going to give me negative 1/2 e to the u plus c. On the left, I'm going to get 1/2 y squared minus ln y plus c. We can put our u back in, so actually let's do that now. This was x squared. Now, our job was to find c. We should have no c's in our answer, so we're going to need to do that. Before I do that, I'm going to move all my c's to one side. So I'm going to have 1/2 y squared minus ln y equals negative 1/2 e to the x squared plus a new c. So again, you can use c1, c2, and c3 there if you'd like. So our next step is to find c. Our initial condition that we were given was x is 0, y is 1. So you're going to have 1/2 1 squared minus ln of 1 equals negative 1/2 e to the 0 plus c. So we get 1/2 minus 0 equals negative 1/2 plus c, or c is equal to 1. And therefore our solution should be 1/2 y squared minus ln y equals negative 1/2 e to the x squared plus 1. We can't isolate y here, so this is the best we can do. So in the previous one, step 3 was isolate if possible and solve for y. But in this one, we can't isolate y, so we're just going to leave it like this. We could also move the 1/2 e to the x squared to the left and make it all equal to 1. That's fine as well. Either one of those would be fine. If we look at our different notations, it says here that we equal 0. That's our differential equation that we start with. It doesn't tell us anything about how our answer has to be written. If you can isolate for y, please do so. But if not, then leaving your answer in this format is fine. Or you can move, again, you can move this term over here if you'd like. Okay. So you might want to try maybe the next one on your own and see how that goes, and come back when you're ready. If you're not feeling confident yet, you can continue to walk through with me. If you would like to go do it on your own, feel free to pause the video and scroll ahead to the answer when you're ready. All right, for this one, it says find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared. So y equals mx plus b would be our equation of a line. We've got this point 1, 3, and we have a slope of y over x squared. That would be our dy dx. So we have dy dx equals y over x squared. Our first step is to isolate our variables. So I'm going to move the y over to the left, and I'm going to move the dx over to the right. And we integrate both sides. I would choose to rewrite my 1 over x squared as x to the power of negative 2. When I integrate the left, I get ln y plus c. When I integrate the right, I should get x to the negative 1, the negative in front, plus c. I'm going to choose to move my c's to the opposite side, so I'm going to get ln y equals negative 1 over x plus a new c. If I'm trying to isolate y, this gives me e to the power of negative 1 over x plus c3 equals y. This can be rewritten as e to the negative 1 over x times e to the c3 equals y. And then I'm going to let k equal e to the c3. Usually if we have our c as an exponent with a base that is a number, we would rewrite it as a new constant. And usually that's represented by k. So you may have noticed that in one of our earlier questions as well. I said let k equal e to the c3. And this is usually convention that if you have your constant in an exponent, we don't know what that constant is, but we know the base is a number, we would rewrite the e to the c as a new constant, and that constant is usually a k. So then we're going to have ke to the negative 1 over x equals y. Now we want the actual equation. Point is 1, 3. So we're going to have ke to the negative 1 over 1 equals 3, or ke to the negative 1 is 3, or k times 1 over e equals 3, or k equals 3e. This means that y is equal to 3e times e to the negative 1 over x, or 3e to the negative 1 over x plus 1. And that would be our final solution. Last one. This is a word problem, as you can see. In the preservation of food, cane sugars broken down are inverted into two simpler sugars, glucose and fructose. In dilute solutions, the inversion rate is proportional to the concentration y of t of unaltered sugar. As soon as we see that proportional, we know from earlier chapters dy dt is equal to ky, and a reminder that this k is the constant of proportionality. If the concentration is 1 over 50 when t equals 0 and 1 over 200 after 3 hours, find the concentration after 6 hours and 12 hours. So there's two different parts here. So 6 hours is one answer and 12 hours is another answer. Okay. So this is a differential equation that we're going to be using y's and t's. K is a constant. So we need all the y's on one side, all the t's on one side when we separate our variables. So I'm going to move dt to the right and the y to the left. We have 1 over y dy equals k dt. We then need to integrate both sides. Again, reminder, k is a constant. So we're going to get ln y plus some constant equals kt plus some other constant. We're going to move the constant over to the right. Okay, so C3 is just C2 minus C1. Then we get e to the kt plus C3 equals y. And as we have with our previous questions, this is going to give us e to the C3 times e to the kt equals y. We're going to let, doesn't matter what you use, I'm going to say let C4 equal e to the C3. The reason I'm not using k here, like I said in the previous question, is convention, is because we already have a k in the question, which is our constant of proportionality. So I can't use k again. So I'm just going to use another c. You could pick whatever you want here, but I'm going to use another c. So then we're going to have c e to the kt equals y. Now this should make sense based on previous chapters. We know that when we had this derivative, dy dt equals k to the y, that our y should be ce to the kt. We know that from our exponential growth decay chapter way back. And so this should not be a surprise that this is what we ended up with as our y. Okay. Now the problem here is that this is not a particular solution. This is a given solution, right? And so it's saying that the concentration is 1 over 50 when t equals 0. So that's our initial condition. Which room do I have here? I'm going to move up here. Okay. So we know that y of 0 is 1 over 50. So therefore c is equal to 1 over 50. And we also know that y of 3 is equal to 1 over 200. So we're going to use this to find k. Because we don't know k, which is a problem. Okay. So therefore, we have y equals 1 over 50 e to the kt, or 1 over 200 equals 1 over 50 e to the 3k. So I get 1 over 4 equals e to the 3k. I can ln both sides. Remember that ln e is just 1. So I get ln of 1 over 4 equals 3k, or ln of 1 over 4 over 3 equals k. And usually we like to leave it in an exact form, so we're going to use that to find our concentration of sugar after 6 hours and 12 hours. So we're finally ready to do that. So A is after 6 hours, or T is 6. So we get y equals 1 over 50 e to the ln 1 over 4 over 3 times t. That is our equation that we're now dealing with, which gives me y equals 1 over 50 e to the ln of 1 over 4 over 3 times 6, or 1 over 50 e to the 2 ln 1 over 4. This is the same thing as saying 1 over 50 e to the ln 1 over 4 squared. And again, reminder, e to the ln x is just equal to x. So this is going to be the same as 1 over 50 of 1 over 4 squared, or 1 over 50 times 1 over 16, or 1 over 800. And you could plug that into a calculator, but you're not going to get an exact answer. If this is on a non-calculator section of something like an AP exam, then you're going to have to be able to work this out, and reminder that that is true to be able to do so. B is after 12 hours. If you haven't paused yet to try this on your own, I would maybe do so now. Try this one on your own. Come back when you're ready. Scroll forward to the answer. If you're still not quite sure about it, you're welcome to continue to walk through with me. I will walk you through the whole answer, but if you are happy with all this, I would pause, try B on your own, and then scroll forward to the answer when you're ready. So again, our equation is 1 over 50 e to the ln 1 over 4 over 3t. This time t is 12, so I got 1 over 50. If I put t as 12 in, I'm going to have e to the 4 ln 1 over 4, or 1 over 50 e to the ln 1 over 4 to the power 4. Using our same property, this is going to be 1 over 50 times 1 over 4 to the 4, which is the same thing as 1 over 12,800 if I do 4 to the 4 times 50. And that is all. So differential equations, if you need to solve an ordinary differential equation, the equations that you have will be separable differential equations. You need to separate your variables, all your y's and dy's on one side, your x's and dx's on the other, or t's and dt's on the other. Once you have separated your variables, you need to integrate. Do not forget your constant of integration. And then you need to isolate and solve for y if possible and simplify. If not possible, then leave it as is. If you are given an initial condition, you need to plug that in to find C and rewrite your answer with no C's left, and that would be your particular solution to the given differential equation.